Hello everyone. In this video, we are going to look at the topic which is mostly for probabilities and stochastics, but it is related and it has applications in engineering. And that is if you have some data from any sensor, anything, and you want to know whether the data that you're getting is a normal distribution or a Gaussian distribution or it's not. Because many times in engineering and many applications, we assume that the data is normally distributed. Like where? Like for instance, if you do a t-test, right? If you do analysis of variance, ANOVA, if you do regression analysis in a standard Kalman filter, in a mixture of Gaussian models, in computer vision, and in lots of other places, you either assume that the data is normally distributed, or if the data is normally distributed, the results of your algorithm would be a lot better. So how can we make sure that the data is normally distributed? If I just have a bunch of numbers and I receive them from any sensor, how can I check for normality of distribution? So here I want to talk about different methods. And the best way to use it is to typically use a combination of these approaches, because any one of them could have some shortcomings, especially the second group, which are descriptive statistics. Okay, so the first group is relatively good. The last group is even better. The second group is limited, but if you use all of them or several of them, you can be sure your conclusion is relatively good. So what are these? The first group is called visual inspection techniques or methods. Okay, the simplest one is to plot a histogram and look whether the histogram of data looks like a bell-shaped curve or not. Okay, so for instance, here I have two different histograms. One is made for data from a normal distribution and the second one from a uniform distribution. And you see here that I kind of see this bell-shaped curve here, but here is kind of uniform. Okay, so I can say, well, this is kind of more similar to a normal distribution, but this one definitely not. Okay, so that's initial visualization of the probability distribution function, PDF, by approximating it by histogram could be your first step. But if you want to do better, you can take advantage of these two plots. One of them is called QQ plot. The other one is called PP plot. So what are these? QQ or quantile plot. This is very common. And this method not only can help you check whether a data is normally distributed, it can check your data against any other theoretical distribution. For instance, if you want to check whether the data is similar to an exponential distribution, or I don't know, a chi-square distribution, or if it's a discrete, a Poisson distribution, binomial, anything, this can work for all of them. So it's not just limited to a normal distribution, although here we use it for that, but this is a very powerful method to check against any theoretical distribution. Okay, so how do you create this plot and how do you interpret this plot? So here on the left, I have the QQ plot for this data on the top for the normal data coming from a normal distribution, and on the bottom right here, I have it for data from a uniform distribution. And the red here, the red dash dotted line, is the one from a theoretical normal distribution, and the blue one is from actual data that I got. And you see that on the left side, the actual data, the QQ plot for actual data, all of these blue basically crosses, they match very closely the one from a theoretical one, the dash dotted red line. Okay, so it's a relatively close comparison from actual data to a theoretical one, but here you see it's not. In the middle is kind of, but as you get away from it, you see that you're getting away from that. And that is because in the middle, you might say, well, actually, if I had this kind of distribution, well, the mid quantiles are quite a bit similar, but when I get to the tails, they do not go down and they still stay high. Okay, so in the lower quantiles and in the higher quantiles, that is where you are deviating from a normal, theoretical normal distribution. And so your QQ plot shows that, hey, this is not a normal distribution. Now, how would you create that? Okay, so this is what you do. Let's say the original data you have is x1 to xn. The first thing you need to do is to sort them, right, from a smallest to the largest value like this. So y1 less than y2 less than all the way to yn. Okay, so you first sort it in an ascending order. Then you calculate the quantiles, both for theory and for the actual data. For instance, how would you do it on theoretical ones? So these are the ones that you expect from the reference distribution, in this case from a normal distribution. So what would you do? In normal distribution, what you need is the inverse cumulative distribution function, or CDF. You need the inverse CDF of the function, or phi inverse. Okay, so if phi is the CDF function of the normal distribution, then phi inverse is the inverse of the CDF of the normal distribution. And if you know that, then if I here is the rank from 1 to n, you have n data, so from 1 to all the way to n, if you have I is any rank, then if you plug it into this formula, I minus 0.5 divided by the total number, and pass it as input argument to the phi inverse, right? And the result of that is going to be the Q that you need to plot versus yi. So here, if yi is here, let's say, if that point is yi, for that, you need a corresponding qi. And the qi is coming from this formula here. Okay, so you pass the I to it, the index number minus 0.5 divided by n, pass it to phi inverse, and this phi inverse is available in tables. Okay, this is available in tables, the inverse CDF function of a normal distribution. You can have it in lookup tables or in built-in functions that use lookup tables, like in MATLAB, in Python, and so on. You can just get the inverse CDF of normal, and that will give you the qi, and then you plot yi versus qi. Okay, now you do that for theoretical data and the actual data, and then for theoretical data, the red line that you see, the angle of it is 45 degrees. So if your actual data here actually matching this line of 45 degrees, this this blue data, then you can say, well, guess what? I have a relatively normal distribution, and if you see big deviations start to show, then you say, well, that is not a normal distribution, or doesn't look like one. So this is how to create a QQ plot and how to interpret that. The next one is called PP plot, or probability plot. This time, instead of plotting quantiles versus data, you plot the actual cumulative distribution function, CDF, against the actual data. Okay, and you do that both for a theoretical distribution and for the actual data. So again, the good thing about this is you can do it for any distribution, not just normal distribution. Okay, again, if you look here on the left, I have it for a normal distribution, and on the right, I have it for the uniform distribution. And you see, in the case of normal distribution, the CDF of theoretical normal distribution and the CDF of the actual data, they match almost perfectly. Okay, but if you look at the empirical ones, you see a bunch of gaps. You see lots and lots of gaps. And as you get toward the tails of the data, you get worse deviations, you get more bigger deviations. So you can say, well, this is kind of not a really great PP plot, but this one is. Okay, so, and again, if you want to do that, it's quite a bit similar process except for the CDF part. So again, if your data is x1 to xn, you sort it in an increasing order, right, ascending order. And then from this y data, now you need to find p empirical and p theoretical and plot them both versus the data itself. So here, and in this case, it's actually yi, not xi, because we are working on the sorted data. So the empirical one for your actual data, the blue curve, at point I and index I, it is I over n plus 1, okay? And then for the theoretical one, you have to get it from the actual CDF of that function. So for a normal distribution, it's going to be the CDF of the normal distribution, which again, you can find from the lookup tables or built-in functions. And then you plot both of them versus, of course, versus your sorted data. And again, for normal distribution, that is going to be the perfect line with 45-degree angle. So again, if you, and it's a curve actually, it's not a perfect line, but this middle portion of it here, this angle is 45-degree. And you see that the whole thing matches, okay, but here the whole thing does not match. So when I say 45-degree, in the case of PP plot, the theoretical one is not going to be a perfect line. In Q plots, it was a perfect line. In P plot, you see it is a curve. Just the middle portion of it has angle 45-degree. So I want you to be clear about this. This is only for the middle portion. You actually need to look at the entire curve, not just the middle portion. So it's better to just get rid of it to not confuse you. So these are two of the important plots plus histogram. And there is another plot called box plot, but I don't think it is anywhere good as these. So to me, if I want to do it, I would first look at histogram, then probably QQ plot. You don't need to look at all of them. But histogram and QQ plot is very good. Now, if I want to look at numbers here, descriptive statistics, right? Not just subjectively say whether the two curves will overlap or not. If you want to look at numbers, one way to look at numbers is descriptive statistics. For a normal distribution, as you know, the mean or average, the median and the mode are all at the exact same point in the middle. Okay, but if your data is not normally distributed, so like negatively skewed or positively skewed, then you see that here your median is between mode and mean in both cases. So if your median, mode, and mean are in this kind of order, mean, median, mode, or mode, median, mean, that is an indication of positively or negatively skewed, and that means your data is not normally distributed. So one thing you can do is just get the descriptive statistics for your data, calculate the mode, median, and the mean, and look whether these three are very close to each other or they are not close. Or since we talked about skewed data, we can look at the measure, the third moment called skewness. And for a normal distribution, the third moment, the skewness, is actually 0. So if you calculate the skewness for your data and it's 0, that means, guess what? Your data is kind of bell-shaped, but in this case, you see that the data is negatively skewed, and in this case is positively skewed, okay? Yes? So that is another way. And you can also look at kurtosis, which is how the thickness of the data. So for a normal distribution, the kurtosis, which comes from the fourth moment of the data, is exactly equal to 3. Okay, so if you calculate kurtosis, and there is a built-in function in MATLAB for skewness and kurtosis, as well as median, mode, standard deviation, all of those, you calculate it for this guy, it's exactly 3. But if it was much sharper than this, so it was something like this, or it was kind of flatter like this, okay, and we call them basically leptokurtic and platykurtic, this kurtosis is bigger or less than 3, okay? So that can also help you. Because, I mean, like, if you come here and look at this kind of uniform distribution, right? If you look at this uniform distribution, well, where is the mean here? Well, the mean is probably in the middle, huh? How about the median? Well, that is also in the middle. So mean and median are both here. How about the mode? Well, there is no real mode. Mode could be everywhere. Here, maybe this one is mode. But they are all very close to each other. So there is no dominant mode in a perfect uniform distribution. Now, if you calculate skewness, what do you think the skewness is going to be? You are right. The skewness for a uniform distribution is also 0, because this data is not tilted to the left or right. So you see, if I just look at median mode, the median mean, and skewness, a uniform distribution can be very similar to a Gaussian distribution. That is not enough. But if I bring kurtosis, because this is flat, this doesn't have any peak or something, the kurtosis here is going to be less than 3. And that is an indication that this is not as bell-shaped curve. It's kind of flat. So that can help, and the fact that mode is not necessarily on the top of those can also help. Okay, so if you want to look at all of these 5 numbers. Okay, that can help you. Another thing that can help you is the range, and that is that box plot thing, right? So, because for a normal distribution, as you know, if this is your average mu, then your data is mostly plus and minus 3 sigma around mu. About 99.7% of your total data is within 3 sigma around mu. Okay, so if you can look at the range of the data and see whether your max and min are close to these numbers, that could be also an indication. Right? If max is close to this number and min is close to this number, that is a good indication. Otherwise, it might not necessarily be a good normal distribution. Okay, so these are kind of numbers that you can work with. But there is a third method, which is even better, and that is to do a hypothesis testing, a statistical testing. So your null hypothesis, H0, is that your data is normally distributed. The alternative is the data is not normally distributed. Now, how can you check this statistics test or hypothesis? There are different ways that you can do it. So there are 4 different tests here. I talk about the 3 dominant one. The first one, which is very common, is called the Shapiro-Wilk test. This is one of the most common and considered tests for normality of the data, especially when the sample size is not big, less than 5,000 data. Okay, so if you don't have a ton of data, this is one of the most dominant tests. Here you calculate the statistics number, W, and then you also have a P, right? You have a significance level alpha, which give you a P, and then with that P and W, you can determine whether your H0 has to be accepted, H0, or not to be rejected. Okay? Now, this is one of the tests, and then we also have the Kolmogorov-Smirnov test, or KS test, which here compares the CDF of your data with the theoretical CDF. Okay, there is a modification of this KS test called the Lilly force, okay, test. And this one is used when you don't have the mean and the variance of the data, but you can estimate them from the data. Okay. And KS is not as powerful as the Shapiro-Wilk test for normality testing. There is another one called Anderson-Darling test, which gives more weight to the tails of the distribution compared to KS, and it's more powerful than KS. Now, I made an application here for you that allows you to load your data either from Excel file or a text file, and then you can plot histogram, QQ plot, or PP plot, and you can do tests for Shapiro-Wilk, KS, or Anderson-Darling. by just clicking on this analyze. I'm going to do it for you. But here, just to explain, this Kolmogorov-Smirnov test, KS test, and this AD test, they have built-in functions in MATLAB, and I'm going to show you. This one here, the Shapiro-Wilk, it does not have a built-in MATLAB function, but I downloaded the file for it from MathWork website, and I'm going to show you that one as well. And just to give you an idea of how these tests are done, I'm going to go into details of how to do a Shapiro-Wilk test. I tell you the theory of it, and then I show you a numerical example how it is done. And then we are going to actually apply the application here, use the application. By the way, as I said, the SW or Shapiro-Wilk test, there is no built-in MATLAB function, but guess what? There is this file on MathWork website, okay, which can give you the result here, okay? And all the credits of that is going to this person here, Ahmed Ben Saida, okay, Department of Finance from Tunisia. I really appreciate what he did, and this code is written quite a bit a while ago. Okay, and these are his references. So all the credit goes to this gentleman for writing the code. I appreciate that. So here, let's go and look at the Shapiro-Wilk test. So how would you do the Shapiro-Wilk test or SW test? So let's say the data you have is x1 to xn. As previous cases, you sort it in ascending order from y1 to yn. So you sort it. Now, with the sorted data, you are going to create the W of statistics. How? So, here, what you do, you first calculate a bunch of parameters called M's. These M's are called the expected values of this parameter Z. MIs are the expected values of ZIs. Now, what are the ZIs and how many of the ZIs or MIs do you have? You have N of them, as many as the number of data points. What is Z first? Z is called the ith order statistic from the distribution that you want. In this case, a normal distribution. So from a normal distribution with N data points, you want to calculate the ith order statistic, Zi, and then find the expected value of that Mi. So what does that mean? First, let's get to the Zi. What does Zi, the ith order statistic, mean? Means the ith smallest value in the sample that you got after sorting. Okay, so you go to this sample that you got, and the ith smallest value, so I2 is going to be, I of 2 is going to be corresponding to Y of 2, right? I of 3 is corresponding to Y of 3, and so on. But in this case, not actual Y of 3, the data that coming from a standard basically normal distributions, because this data might or might not be from a normal distribution. So you have to generate data similar to these Y's. These are coming, let's say, from your sensors, but now you go to a normal distribution, and with the sample size of N, you take a sample. So you take a sample of N from a standard normal distribution, which means average 0 and mu of 1, and you sort that data that you got, the N data points that you got from the standard normal distribution, and then the ith smallest value is going to be Zi. Now you need the expected value, the average of that over so many samples, and that is called Mi. Now you might say, how do I get that? Because you have to sample a normal distribution, and then you have to do it a bunch of times so you can get an expected value. So these values are typically pre-computed. They use Monte Carlo simulations, and they calculate these pre-computed. They are available in statistical tables. Or you can calculate them numerically, but in this case, we have tables like this that you can go to them, and these tables are there to give you exactly the thing that you want. Okay, so for instance, if you have 10 data in your sample, let's say that you got 10 data and you want to check their normality, you go to n of 10, and then, as I said, you need 10 m's, correct? Where do you get these 10 m's? Well, here, look, I need 10 m's. These are my 10 m's. This is the first one. This is M1. This is M2, all the way to what? To M10 if n is 10. And these tables are getting bigger and bigger. Okay, so it's just a portion of the table. For bigger n's, you have basically extended versions of this table. So you get the m's from these tables. Okay, you don't need to do all those calculations. They are typically done for you. You can just get them. Now that you got the m's, you need to calculate two things. One is V, the other one is A's. The V here is the covariance matrix from these m's. Okay, so if you calculate the covariance matrix from these m values, that is your V, which here you use inverse of it. And then for each m, you calculate a corresponding I. So if I plug in any m in here, that will give me a corresponding I in this formula. And these guys have some kind of symmetry in them, these A's, like A1 is the same as A negative N, A2 is the same as negative AN, I'm sorry, A2 is the same as negative AN minus 1. So they have a symmetry with, of course, a negative sign. So you don't need to calculate all of them, you just need to calculate half of them. Okay, and there are N of these A's, okay, which come from these M's. So once you have these M's, you calculate these A numbers from this formula, and as I said, V is what? V is the covariance matrix of these M's. So that is the covariance of the M vector, and M vector is this. Okay, so you calculate these A's. Again, most of the time you don't even need to calculate the A's. These A's are typically pre-computed for you for different N sizes. Okay, so for N of 10, if you want different A's, guess what? You have different A's. And look here, I should have 10 A's, but I only have 5 of them. What about the other 5? As I said, these other 5s are symmetric with respect to the first 5, except with a negative sign. So if the first one is negative 0.57, based on here, the last one here, A number 10, is going to be negative 0.5739. If this one is negative 32, then the ninth one is negative 0.3291, and so on. So these, if you mirror these top 5 and negate them, you'll get the bottom 5. Okay, so now that you have all of these A's, you go ahead and calculate your W statistics by this formula, where in the numerator you have basically a weighted sum of the original Y's weighted by these A's, and then the whole thing squared divided by the variance of the data. Of course, there is no denominator here, but it's basically sum of this squared, the sum squared deviations, right? So every data is subtracted from the average of the data squared, and so this is sum squared differences, and that is the squared of the weighted data. It gives you the W statistics. Now that you have W statistics and you have a significance level alpha of something, 0.01, 0.02, 0.05, with some alpha value and W, you can calculate your p-value, and then with p-value you can accept or reject the null hypothesis. Now here is a table that you can use for finding the p-value given the alpha and the W. And this table is coming from this website, by the way, okay? So this table is not mine, it's coming from some common textbooks, okay? So this is from this method that was developed about 60 years ago, okay? And still is very powerful and useful. So here for different N's and different alphas, you get different W values, and then with the W values, you can calculate your statistical W from there, and check whether you can accept or reject the null hypothesis. Okay, and you can also read P, but look here, If I want to give you an example, let's look at some numbers here. So let's say in this case, I only have 3 data. Now, of course, 3 data is really hard to say whether data is normal or not, okay? But let's say I only have 3. First, I sort them, so it becomes like this. I also need to calculate their averages later for the denominator of W. From n of 3, I go ahead and read all of my 3A's, okay, which I can get from any table. Look here. So n of 3, right? So you can get these numbers from the tables. Look here. You can see this number, and then you can see these two are negative of each other, and the middle one that is not given is 0. When it's not given, that means it's 0. So you calculate the weighted sum of the y's, you calculate the denominator, you square that number and divide it by denominator, and you get this number. Now, one thing to know about W, this W number should always be less than or equal 1. Okay, so here, the fact that you got a little bit over 1, that means you did some numerical mistake. This should not be 1.01. If you actually do it correctly and don't do all of these truncation errors and something, and you do it properly, your number here is about 0.98 if you use a lot more decimals. So my number of W is 0.98. Now, before I even go and look at that table, one thing I want to tell you is this. If your W number is close to 1, very close to 1, that is an indication of normality of data. If the number gets further away from 1 and gets smaller, then that means you're moving away from a normal distribution. So the closer the W to 1, it's a better indication of normality, okay? Keep that in mind. Now, you can guess, in this case, with the number I have 0.98, that is a very good indication of normality, right? But how can I use this table? For this table, I have n of 3, and if I use a 0.05 significance level, alpha of 0.05 in this case, then the number that I need the W to be at minimum is 0.767. So if the statistic W that I have is bigger than 0.767, that means, look at this W is bigger than that. Because it is bigger than that, and I don't even need this part, okay? This is my W of the table. Because my W statistics is bigger than W of the table, that means I can accept the null hypothesis. And I can say the data is normal. If it was less than or equal that, then I would reject the null hypothesis. Okay, so we don't even need to care about P. We can just compare W versus W of the table. Or we can interpret this number as the p-value. Okay, so this is how you run a simple Shapiro-Wilk test, and you can use it on a lot more data points than just 3, but what you need to have is some kind of software that does this lookup for you from a table like this and from a table like that. So it has to give you the A's and the W's and with N, and then does some calculations for you, and then accepts or rejects the null hypothesis. And that is exactly what this function is doing in this case. So this is the app, as I said, that I wrote, and you see that when I run this app, it brings this window up, right? So let me run it again for you. So it gives me that window, that application, and that application now allows me to browse for the data. So I go ahead and browse. Now here I have the normal data and the uniform data, okay, in 2 different formats. So let's first run the normal data that I exported to a text file. It gives you a success for loading, and so you're good. Now if you want, you can start with histogram and Shapiro-Wilk test and do the analysis, and that should give you the descriptive statistics, the result of Shapiro and the histogram. As you see, the histogram is almost normal. If you look, your mode, your median and your mean are the same number. Now, mode can easily throw you off, okay, because this is the place that data gets some maximum, and it depends on the mean. So mode alone could be misleading, but the fact that median and mean are very close, that's one good start. The fact that your skewness is close to 0, your kurtosis is close to 3, these are good starts. Here I calculated mean minus 3 standard deviation and mean plus 3 standard deviation, and I also have my mean and max of the data. And you see that they are not far apart from each other. Okay, so that is a good indication in terms of descriptive statistic that the data is normal. Histogram looks like a good one, and your Shapiro-Wilk test says the distribution is normal. Now, if you want to do a QQ plot, go ahead and change it to QQ and rerun it. And there we go. You see that the actual data and the theoretical ones matching relatively well. Or you can do a PP plot if you want. There we go. You see, they are relatively matching almost perfectly. So this is a good indication that my data is normal. If I don't want Shapiro-Wilk test, I can go to KS test, or I can do the Anderson-Darling test, and I can do the test as well here. And you see, for instance, it says this one is also normal. Okay, so this is how you run this test, right? Let me run it fresh again for you, and let's this time, you don't need to close it and open it like I did. I just showing you on a fresh data. So this time I'm uploading the uniform data from my Excel file, and again it is working fine. And then again analyze it. You see the histogram clearly not showing. You see that Shapiro-Wilk says it's not normal. If you see the median and mode, look, they are close to each other again. Skewness is almost close to 0, but look at your kurtosis, it's about 1.8. That's not a good indication. Okay, even the range is not super bad. So here the only tip-off is kurtosis. The histogram is much better, and this test easily rejects it. And if you look at QQ plot, also you see the deviations here at the tails, or the PP plot. Okay, so these are all sorts of things that you can do, and I give you a zip folder which has these 2 files in it. Again, this code is not mine, so that code, the credit of that goes to this person here, Ahmed Ben Saida. And I put both of these in a zip folder along with these 2 sets of data for you to play with. Feel free to generate your own Excel file or text file and use this application and check whether your data is normal or not before you use it for any application, any algorithm, anything that assumes the data is normal. Make sure first it is, then use it. Okay, otherwise you have to use other methods that do not have that assumption. So hopefully this video was useful to you. I'll see you in the next lecture. Thank you.